Hello everyone. The research paper that we are going to talk today about is titled as Temporal Fusion Transformers for Interpretable Multi-Horizon Time Series Forecasting. Now these terms, for example, interpretable, multi-horizon, transformers, we will be going to decode them in a very short interval of time. So yeah, let's hang for a moment. This paper was published by a collaboration between University of Oxford and Google Cloud AI team. Brian Lim from University of Oxford and these other three guys from Google Cloud AI team collaborated to target these time series forecasting problems by attaching the attention mechanism to it, and it provided a novel architecture which handled or tackled these time series problems very efficiently. Now, what they did, what their technicalities was, what were the novelties in their work was, we are gonna see it in the next slides. So yeah, let's start. So when we talk about this time series forecasting, we are referring to the process of predicting these future values or these patterns between the variables based on their historical behavior. In time series, data points can be recorded in a sequential order, but in a regular intervals. They can be in hourly, daily, monthly, or we can say in a yearly basis. Our goal is always to analyze the historical data and use it to make the accurate predictions about the future values. But we are doing these problems for a very long time, from the time we are using machine learning to tackle these issues. But there are very crucial, misunderstandings, or say we can say drawbacks associated to our approach. For example, there is a heterogeneous nature of available data sources. Our input features have a heterogeneity between them. We always, in our traditional frameworks and in our traditional models, we always treated our input data as a lump. We treated our n number of features like a same, but our feature were always different. Our input variables were always different when we are giving a forecasting model or we are making a forecasting model. For example, if a model has let's say 5 to 6 number of input variables, then some of the input variables will hold a temporal dependency within it. Some of the input variables will hold a spatial kind of disturbance or variability between it. So these capturing these spatial and temporal dependencies with a normal or with a traditional framework was not possible. It needed a very unique framework to capture these dependencies. And also there was a interaction between these features, these different kind of the nature between the input variables, and the capturing the interaction between these different input variables was not these our traditional machine learning models and deep learning models were not able to capture these complexities between our input data. So we needed a very strong or robust model to capture these dependencies. Now, what happened is from very long time, these deep neural networks are outperforming our machine learning models, and from many years we have getting new frameworks which are outperforming the previous methods also. But yeah, the one thing we can say very surely is despite performing that good, the interpretability always remain challenging for these models. Now, what do you mean, or what do we mean by we say this term interpretability is, let's say our model is predicting the weather of a uh, of a location. So if our model is interpretable, we can find out, okay, if a model is saying that it will be raining today, then on what feature or on what variables it is saying that this will be the output or this will be the prediction of our model. So this interpretability is making our model more transparent. It is increasing the confidence in our outputs. It is making our model more trustworthy, more reliable. So this interpretability was very important from a very long time, because all our deep neural networks, our machine learning models, the basic criticism they faced from these n number of years was they were like a black box models. And whenever our state agencies or national agencies are making a system or making a prediction model which is gonna affect a large amount of uh, you know mm, basically affecting our country on a very large scale economically or agriculturally. For example, let's say we are making a weather prediction model or a model for our healthcare or our economy. So they cannot trust the black box model. The model should be very transparent about its outputs, and it should be transparent about its prediction capabilities and its prediction kind of analogies. So yeah, there were some techniques like line and shape that we are using from now 4 to 5 years now very effectively. But these methods are some post hoc approaches, and they would lead to a very poor explanation and a very poor explainability. Why? Because first, line was a surrogate model, and it basically, both of these methods basically ignores the time ordering of the input features. And the models which are kind of ignoring the time featuring of input features, how they can be reliable in making our model interpretable. So interpretability is kind of a thing which should be inculcated, or we must say should be added within our model, within the we can say the methodology or the basic framework of our model. So all these kind of issues were handled very effectively in our temporal fusion transformers. How they do it? But first, we will see how the related work or how the previously done work helped us and kind of led us to find a optimal solution for our problem. So let's see the work done in this field till now. Okay, so when we talk about the recent works that has been done for the time handling these time series forecasting problems, then all the work can be basically categorized into two categories. The first was these iterated approaches, and the second one was these direct methods. Now, what are these? We will be kind of talking them one by one. First, when we talk about these iterated approaches, so they basically utilize these autoregressive models. For example, you have been using things like ARIMA or ARIMA-based models like things. Now, in these autoregressive models, predictions are made by recursively feeding the previous predictions into our future inputs. So they will utilize sometimes, we have heard these LSTM networks or DSSMs, which are also known as these deep state space models to generate the only one step ahead predictive distributions. Now, these one step ahead predictive distributions are provided here. Now, which are then used to recursively generate these multi-step predictions. What does it mean is when they are using their mechanism, they are only producing a one step ahead prediction, but these one step ahead predictions are then categorized and then reused to provide us with these multi step ahead predictions. So what the issue has been with these methods are we can say that these iterative approaches have been effective in some cases, but they rely on the assumption that the values of all the variables or all the input variables that we are using in our model and except the target variable are known at the future time. And I know this here is the issue where it is affecting our mechanism, because this assumption basically restricts their effectiveness in the practical scenarios, because in practical scenarios there will be numerous useful time varying inputs are there which exist, so with many being unknown in advance. So having this assumption basically is a drawback with these iterative approaches, and we need to see for a good method which will be dealing with these time varying inputs with a more effective way. Then when we talk about these direct methods, so in direct methods what happened is we just give a series input and got us input output in series also. In in description we can say it is a time series forecasting methods that are designed to explicitly generate the forecast for multiple predefined horizons at each time step. These methods employ these sequence to sequence models. For example, we have heard these LSTM encoders to summarize the past inputs and generate the future predictions. So, here is the basic distinction between these iterative and these direct methods lie upon. So, One example of these direct methods is this multi-horizon quantile recurrent forecaster, NQRNN. All these methods that I'm talking about, the comparative study of them with our temporal fusion transformer will be shown in the result section. So you should be getting the hang of them. So these NQRNN which I'm talking about, they uses LSTM or convolutional encoders to generate these context vectors, which are then fed into multi-layer perceptrons, MLPs, for each forecast horizon. So these directly methods generally outperform these iterative approaches in terms of accuracy. Because as we know that the basic assumption that these iterative approaches were working on were causing a serious kind of, we can say, a misunderstanding in terms of handling the inputs. So we can see that how these direct methods are advancement over these other iterative approaches. And the method that was discussed in this paper, that is this temporal fusion transformer, hence there is a novelty come in this method because it explicitly considers the diversity of inputs and naturally handles both static covariates and these time varying inputs. So it basically incorporates separate encoder and decoder attention mechanisms for static feature and self attention for time varying inputs. How this is being done, we will see when we are discussing its architecture in detail. So yeah, let's move forward and see how its architecture is made. And but yeah, before dwelling into its architecture, the first thing is, from 5 to 10 years, whenever we heard about things or time series forecasting issues, we see the only thing that ruled this era was these LSTMs. So why not we are using this basic LSTM mechanism, and why we have to change our approach to a transformer based model? Why we need attention? What is so special about transformers? So yeah, let's delve into that and find what's so special in these transformers. Okay, so when we talk about these things, that why transformers and what is the need of transformers to be introduced in this section. So the first thing is this architecture of transformers that we all familiar about, because when we seen this research paper, attention is all you need in 2020 2018 from this Ashish Vaswani. So yeah, now what was so special about this attention mechanism? Why we need transformers in this context? So, as we know, the field of deep learning continues to advance. These transformer-based architectures have emerged as a game changer in various domains. As these architectures were originally introduced for these natural language processing tasks, offer unique advantages over traditional approaches. So, in this context, we will explore the key reasons why there is a growing need for transformer-based architectures. Focusing on their ability to model these long-term dependencies, their attention mechanism, their parallel processing capabilities, and also there are a number of benefits. We will see them one by one. So first, when we see that when the issue comes about modeling these long-term dependencies, then our traditional recurrent neural networks RNNs, such as LSTM or GRU, they struggle to capture these long-term dependencies due to their sequential nature. So whenever we are, when we have to capture these long-term dependency, one thing was clear that we cannot handle them sequentially. We have to opt for a different mechanism, which are, using a better mechanism to capture these dependencies. So in contrast to that, transformer-based architecture excel at mostly modeling these long range dependencies by employing this special self attention mechanism. Now, what this self attention mechanism mathematically is, I will be telling you in the next slides, so don't worry about that. Self attention basically allows each position in the input sequence to attend to all other positions, enabling the model to learn the context and relationship of different elements more effectively. This ability to capture long-term dependencies in crucial and various applications, including natural language processing and time series forecasting, etc., and image recognitions, may make our transformers a very good choice for these kind of problems. Now, the next thing is why this attention mechanism is a good option when it comes to better context learning. So one of the fundamental components of our transformer was this attention mechanism. Attention allows the model to assign different weights or importance to the various parts of the input sequence. So basically we can identify the major basically input variables which are affecting our output majorly. So this mechanism not only enhances the model's understanding of the input, but also enables it to focus on the relevant information. So by leveraging this attention, transformer-based architectures can learn the intricate patterns and the relationship in the data, leading to the improved performance and accuracy. Now, the third benefit that we get from our from our transformer is this parallel processing. Now, what this parallel processing means is this was the we can say the advantage of using transformers, because when we talk about parallel processing, then unlike our sequence models like RNNs, transformers can process inputs in parallel, making them highly efficient. These parallel processing capabilities stem from self-attention mechanism, which allows the model to simultaneously attend to all positions in the input sequence. So see how it makes things more fast and more effective. As a result, transformers can process the long sequences in parallel, reducing training and inference times significantly. This advantage is particularly valuable in applications that involve large data sets. For example, in our issues when we are dealing with these time series forecasting problems, and which involves the real-time processing, and where speed is very crucial, we cannot waste any time there. So in that cases, these our transformers were very effective. Now third thing was, or fourth thing was, which are effective, was this transfer learning. Now another remarkable aspect of our this architecture was the transfer learning. How? Because they are often pre-trained on massive data sets such as ImageNet or large text corpora, or and they learn the journal patterns and representations. Now, this pre-training allows this model to capture the rich feature from diverse data sources. These pre-trained transformers can then be fine-tuned on specific tasks with a comparatively smaller data sets. And we can use these data sets in any other location, or we can adapt them for any other, variable inputs which have the similar nature like ours. And this transfer learning approach saves computation time and data requirements, enabling the model to perform well even with limited labeled data. And then yeah, we also know how there is a benefit of fast training, inference, and processing, because due to their parallel processing nature and efficient attention mechanism, transformer offers this fast training, inference, and processing. Their ability to process data in parallel and capture long-term dependencies more effectively leads to quicker convergence during the training, so which make them more faster. And also they can effectively process the large amount of data during inference, making them suitable for our real-time applications and large-scale deployments. Now, it is totally clear that why transformers were adopted, basically how why transformer-based approach was targeted while we were solving these time series forecasting problems. So yeah, let's see the next aspect of our research paper. Okay, so as from now on, or from from very long time, we are discussing that how these temporal fusion transformers are providing us with this multi-horizon forecasting. Sorry. So when we talk about multi-horizon forecasting, we have also a issue of diverse inputs. So what happen is, in multi-horizon forecasting involves predicting variables of interest at multiple future time steps, offering users access to estimate across the entire forecasting horizon. This ability to look ahead and optimize actions at multiple steps in the future is incredibly valuable. And think of retailers optimizing their inventory for an entire upcoming season, or clinicians optimizing treatment plans for their patients. So it has a long, we can say, application part. So the application of multi-horizon forecasting are vast and impactful too, ranging from retail to healthcare to economics. Now, what are the problems with this? The first is our input variables are having very diversity in them. For example, the the our input variables can be categorized into two categories. The first are these static ones, and the second are time varying. For example, there will be some input variables which are remaining constant throughout the time series. They are not changing within the stations, and there will be some inputs which are varying with time. Now, the inputs which are varying with time can also be categorized into two another subparts. For example, one which will be unknown in future. Now, future is the time interval we are considering, for which we are providing a forecast. That is time interval after time t. And there will be some time varying input features which are known in future also. For example, which will be known after the time t also. So how this thing is taken care in case of our temporal fusion transformers? So yeah, first we will be knowing more about what about these diverse inputs and what is the importance of these diverse inputs. So in practical, what happen is when we talk about multi-horizon forecasting application. Now, multi-horizon means we are providing you the outputs at a at multiple time steps ahead, and we are while we are dealing with multiple variables, so providing you with the distribution of outputs at a multi-horizon mean a multiple time step ahead distributions outputs is more crucial. So when we are doing these things, we often encounter diverse data sources, each providing unique information about the future. These sources may include the known events, for example, upcoming holiday dates, other exogenous time series such as historical customer foot traffic, and static metadata like the location of a store. However, the challenges lies in the fact that we have little knowledge about how these data sources interact with each other. The heterogeneity of these inputs combined with the lack of information on these interactions make multi-horizon time forecasting particularly very challenging. So, multi-horizon forecasting seems to be very kind of, you say, promising in future, but doing it is a very challenging task as compared to image processing, etc., task, etc. So why there is an importance of diverse inputs? So despite the challenges, incorporating these diverse inputs is essential for us, because to achieve the accurate and reliable multi-horizon forecast, these inputs provide the valuable context and information about the factors influencing the variables we are trying to predict. By leveraging these diverse inputs, we can uncover, we can say, the hidden patterns or identify correlations and capture the complex dynamics of the forecasting problem at hand. This holistic approach allows us to make the better informed decisions and optimize our actions across the entire forecasting horizon. So here we can see the how multi-horizon forecasting is a better way to deal with these time series forecasting issues, because to tackle the challenges posed by these diverse inputs, researchers have developed advanced techniques and models, from which these temporal fusion transformers are also among one of them. So it was a crucial, we can say, problem while we are dealing with these time series forecasting issues, but it allows us to optimize our actions at multiple future steps. And the presence of diverse inputs, including known future events, exogenous time series, and static metadata, poses unique challenges. However, by embracing these diverse inputs and developing advanced models, we can uncover valuable insights and perform make a better model which can deal with these time series forecasting issues more effectively. Now, how this model is composed, basically what is architecture is saying to us, or what's so important and novel about it, we will talk about it in the next slide. So let's move ahead. Okay, so when we come to temporal fusion transformers, we have some major novelties like gating mechanism, the variable selection networks, static covariate encoders, our temporal processing, and our prediction intervals. I will talk to about about them one by one. But first, let's see the architecture of our temporal fusion transformer. So what happen is, as I talk about the diverse inputs, our temporal fusion transformers deals with it very implicitly, or we can say very categorically. For example, you can see static metadata inputs which were known up to the time t only, and the inputs which are known up to the future times ahead also. These three types of inputs are fed to our network in three different ways. For example, you can see these color changes here. These color changes says that they are encoded differently. So you can see these LSTM encoders have also shown with a different color in these three different subparts. So it mean is, to providing them with different encoding or to the different parts of our architecture, basically provides or give the information to our model that how these inputs are differentiated in time, because these inputs are not the same. They have different characteristics, and they have very, you can say, very different nature, so that that can be inculcated into our model, or you can incorporated in our model, so that it can predict in a better way. Now, what's another better things in our, we can say, TFT is, the first thing is the gating mechanism. So when we talk about the gating mechanism, our model incorporates this mechanism that provides it the adaptability and the flexibility to the model's architecture. This mechanism allows us to dynamically skip over unused components and adjust the depth and the complexity of the network based on the specific dataset and scenario. Basically, it tells about how much of input should be given, the non-linearity should be incorporated into that or not. And this adaptive nature ensures that TFT can effectively handle a wide range of time series forecasting tasks, accommodating both simple and complex patterns in the data. Now, next thing was this variable selection networks. Now, when we talk about this variable selection, now what this variable selection does is it basically plays a crucial role in selecting the relevant input variables at each time step. By dynamically choosing the most informative features, TFT focuses its attention on the inputs that have the greatest impact on the target variable. These feature selection capabilities enhances the model's accuracy and efficiency, and it avoids this unnecessary computation or irrelevant variables, discard them, and optimize the use of our computational resources. So that was a major, we can say, the novelties, or kind of, we can say, the efficiency or efficient way of TFT to handling these diverse inputs. Third thing is our static covariate encoders. So to incorporate the static feature into the forecasting process, our model utilizes these static covariate encoders. These encoders encode the static information into context vectors, which are then integrated into the network. By conditioning the temporal dynamics on these context vectors, our model captures the influence of static covariates on the time series data, and this integration allows the model to exploit the valuable insights provided by the static features and enhances its forecasting accuracy. So, especially in scenarios where the static factors plays a significant role into our forecasting problems. Now, when we talk about the static covariate encoders, the next thing comes is, what is this temporal processing? So temporal processing basically tells that our model is basically, better in learning both long-term and short-term temporal relationship from observed and known time varying inputs. For local pressing, our model employs a sequence to sequence layer, which captures our immediate dependencies within the time series. Additionally, it has a novel interpretable multi-head attention block to capture these long-term dependencies that you can see in the figure. And this attention mechanism allows the model to effectively capture these temporal patterns and dependencies that span across multiple time steps. So by considering both local and long-term temporal relationships, TFT achieves a more comprehensive understanding of the data, resulting in accurate and reliable forecast. Now, what is the next thing that was novel to it? That was the prediction intervals. As I told you, when we talk about the prediction intervals, our temporal fusion transformers are basically providing us the quantile forecasts that is they are basically, in nature they are providing a distribution of our outputs. They are not giving us a deterministic output, but basically they are providing us with a distribution at different quantiles. For example, 10, 50, and 19th quantile. They're providing us with the distributions, so that we can get a better idea of how our model is working. Okay. Now, these prediction intervals basically are provided through these quantile forecasts, which offer the valuable information about the uncertainty associated with the predictions. Because the prediction intervals indicate the range within which the target variable is likely to fall at each prediction horizon. This measure of uncertainty allows the decision makers to assess the level of confidence in the forecast and make informed choices based on the associated risk. The inclusion of the prediction intervals enhances the interpretability of the forecast, and you can say that it enables users to incorporate the risk management strategies in their decision making process. So it basically tells that how our TFT mechanism or architecture was so novel, and what was the benefits or the major constituents of its mechanism that make it so novel. So yeah, now next let's move to the advantages or the major advantages of TFTs that it provides us while dealing with time series forecasting problems. So yeah, in short, if we have to basically summarize the temporal fusion transformers benefits to handle these time series problems, we can come up with a number of benefits. But let's summarize into them 5 to 6 topics. So yeah, the first thing is handling this diversity of inputs. So our model handle the diverse inputs, including both static covariates and time varying data very effectively, and it incorporates its static covariate encoders to basically effectively integrate the static features into the forecasting process. This enables our model to leverage additional information that can have a significant impact on the predictions. By considering both static and time varying inputs, our model can capture a comprehensive view of the underlying patterns and dynamics in the data. Now, the next thing is this interpretable attention mechanism. So when we talk about this interpretable attention mechanism, how it works, I will be telling that very deeply in the next slides. But basically, it utilizes an mechanism which allow users to gain insights into how the model makes predictions. The attention mechanism identify the important variables and components within the input data that contribute significantly to the forecast. This interpretability aspect is valuable as it provides transparency and helps users understand the underlying factors driving the predictions. So, by examining the attention patterns, users can gain insights into the temporal dynamics and the relationships between different variables. So, it is one of the selling point of this our TFT mechanism. Next things was is identifying the important variables for prediction. So yeah, our model basically captures or identify the important variables for predictions by leveraging the variable selection networks, and we can say that it dynamically selects the input variables at each time step. This feature ensures that our model focuses on the most influential factors while disregarding our irrelevant inputs. So when we are dealing or basically what in short we can say that kind of encountering these time series forecasting issues, we have a number of inputs that are varying for a very long time. We have huge data sets. So basically identifying the important variables and which are affecting our predictions are, it is a crucial step, because without that data engineering or feature engineering, you cannot be giving your, if you're not giving your model the information that is more reliable or more important to provide the prediction, and if you're not feeding your model in a better way, then you cannot expect miracles from it. You have to have give its the input in a much understanding way, because your model is like a machine, and the user, you are giving input to it, so that input is a more understandable way. You have to basically liquidize it in a manner that your model can feed from that information and give you more reliable outputs. So yeah, our model has that capability, but still it depends upon the user's capability to feed the model more effectively. Now, the next thing is this capturing the persistent temporal patterns. Now, TFT is designed to capture these both long and short-term patterns present in our time series data. So, with temporal processing capabilities, our model can effectively learn the dependencies and the relationship between past and future observations. So, the interaction part that we talk about in the input parts, we are coming into that. It is handling that interactions very effectively due to this attention mechanism that is has been added into its working. So what happens is it allows the model to capture these persistent temporal patterns such as a seasonality or a lag effects, which are crucial for accurate forecasting. So by accounting for these patterns, our model enhances its forecasting accuracy and provides us with more reliable predictions. So yeah, it is one of the major kind of, we can say, the benefits, or the major, we can say, the important features and the novelties that our TFT brings into our focus. And yeah, the other major contribution, or we can say better thing, was this gating mechanism for our irrelevant inputs. Our model enables it to adaptively skip over this irrelevant input, and this feature enhances the model's ability to handle these noisy or unnecessary variables that may not contribute significantly to the forecast. So by negating the impacts of these inputs, our model improves the efficiency of the forecasting process and focuses its attention on the most informative components of the data. So yeah, so it's totally includes that why our TFT architecture is, basically handling all the issues or all the drawbacks of our approach, and our architectures that we have used in the recent times, and also the drawbacks that we talk about our approach. It is handling all of them very effectively. Now, what is this interpretable attention and all these things? We will be talking them in the next slides. So yeah, let's go to that now. So, okay, before diving into our, interpretability and how it has been, our attention mechanism have been made interpretable, I have to, I wanted to give you a slight idea of how a model is working with the inputs, and how in a very concise way it's handling those inputs into it. So, yeah, as you can see here, our y cap qt tau is equal to function fq, which taking as inputs what? Tau uh, yit to k time t, then zit to the k time t, then xit to the k times t plus tau, and si. Now, what these variables mean one by one, let's go into that. Our y cap qt tau is nothing but it is about the quantile forecast that we are providing at tau time steps ahead from time t, and the q's refer to the qth sample that we are providing the our prediction for. So the y cap is basically the prediction that we are providing from our model. Fq is basically the prediction model or the function which is taking all these inputs and providing us with the y cap. So fq is basically our model, or we can say the relationship that we have formulated from our model. And tau, as I told you, tau is nothing but it is the number of time steps ahead from time t that we are providing the forecast for. And yit to kt is the target information within the finite look back window k. This look back window k is basically the encoding length, the time period we are giving our model to see into behind the time, so it can have this temporal attention into it, or basically it can capture these temporal dependencies of the data. So yeah, YIT is the targets, or basically the known outputs up to time t. Okay, up to time t. Now what is more important is, let's change the color. So yeah, this zit and xit, these both are the input variables. Okay, these both are the input variables, but what's important about them is the z inputs that we are talking about. These are unknown in future. That's why they have only they have only known from the look back period of k to the time t only. But when we are talking about this x, these are the inputs which are known in the future also. That's why they have been given a time interval from a look back period k to the t plus tau. So it tells about how it is handling these diverse inputs, how this input is given to a model. And yeah, in the end, SI is nothing but it is the static variables that are not changing with time. As I told you in the previous slides, how our input variables were differentiated into the static and time varying. So yeah, SI is telling us about the static variables from that slide here. So yeah, it basically summarizes that how a model is taking all these inputs, okay, and providing, making basically incorporating a relationship over them, and providing us with the quantile forecast at the q example with the a time step ahead that we need information up to. So yeah, that's all about our diverse inputs and the quantile forecast of our TFT model. Now what is the interpretability that I'm talking about all the time long? So yeah, let's switch into that. So yeah, it is the most important aspect of this paper, because the very important thing or very novel thing they did was, when we talk about transformers, the thing we know about is a multi-head attention. We all know about it, what a multi-head attention is and how we use it, why it is so significant. Okay, but the issue with multi-head attention is it was not interpretable. So when we are getting results out of multi-head attention, that we know in our transformer paper, that is attention all you need. We discussed it in that paper, that was in 2018, I think. So yeah, that multi-head attention is very good while it is capturing these dependencies of our data in the previous time steps, or we can say the previous inputs. It was very effective, but the only issue was it was not so interpretable. That much of interpretability it doesn't have. That once we get the outputs, we can backtrack which kind of variables are affecting these our predictions or our outputs. To know that, or to make that attention mechanism useful and also interpretable, our temporal fusion transformer mechanism basically make it interpretable. How they does it, let's see that. So yeah, interpretability was incorporated by a simple mathematics they did is, because as we see from our interpretability, yeah, so our attention mechanism was nothing but it was as we know in our attention mechanism, there are these three matrices, that query, key, and value matrices. We get the dot product from query, key, values, these matrices, and then we multiply it with the relevant these value matrix. And what this thing we get, this is on our other attention head. We just form a normalizing function, which we generally use a softmax into that. This is for the scaling thing, and this is basically a attention head that we get. Now, in the basic transformer architecture, what we did was, generally we took these attentions from multiple heads and concatenated them, as we've seen that h1, h2, h3. H1, h2, h3 are nothing but just they are the, we can say, the pair of the query key and the value matrices. Now the different pair of query key and value matrices tells us about the different multiple heads. Okay, different heads. So when these heads provides us with the attention matrices, and when these attention matrices are basically concatenated, we call it as a multi-head attention. Now this multi-head attention was used in our basic paper of transformers that we talked about. But as we know, the issue with that was this concatenation that we are doing here was not that much of interpretable. So to make it interpretable, what they did was, this whole term concatenation was replaced with h tilde. Now what this h tilde was, this h tilde was nothing but it is simply what they did in this formulation was, they take a shared value matrix. Okay, the value matrix was taken as a shared value. So it and these attention matrices, that is the the dot product of the query key values matrices, we despite of doing concatenation of them, we did what we did was, we did the additive averaging of them. Okay, by doing additive averaging, this this value matrix that we're talking about, we have taken it the shared value, so it will automatically come out. And this additive aggregation of these attention matrices, when it's done not concatenated, and they have done in an additive aggregation of them, this whole thing was more, you can say, interpretable as compared to this concatenation. Now why it is happening, so you can think it of in a sense that, let's see, we have three features. So yeah, let's sort it out. We have only two features. Both of them have very high attention value when we are comparing them with our output. But just because one of the feature have very a low value metric score, its attention value is getting discarded. So this attention value should not be kind of ignored, or what you should say, should not be getting vain, because our attention mechanism is working so hard and we are incorporating that into our model. So to resume or to keep that basically attention mechanism alive and to basically backtrack it, once we get the output, we do this additive aggregation of our attention heads and not basically concatenating them. So in to summarize all that up, basically what they did was they get these attention weights, okay, and then in spite of providing with the different value matrices for different features, they use the shared value matrix. So these shared value matrix comes outside of this additive aggregation, and when we, in place of providing them with the of concatenation, when we did this additive aggregation, our whole attention mechanism was more interpretable as compared to the standard transformer network. So yeah, this interpretability into our attention mechanism was the key point and was more effective to identify if our model is working fine, how it is giving our outputs, is these outputs are reliable or not. So yeah, it was the major input, or we can say it was the major novelty of this paper, that they make this attention interpretable. Now yeah, next we will see that how this model was trained and how this validation and the comparison scores with other models was. So yeah, let's move to that now. So yeah, while we talked about evaluating the performance of our architecture, so to evaluate this architecture, we need different type of data sets. So that we know that what kind of the outputs our model is giving for different kind of inputs, which contain different type of variables and different type of output nature. So the type of data sets used were these four. The first was an electricity data set, which were containing the data of US 370 US households. And in this basically model, what we did was we take the look back period that we talked in the architecture time. The look back period was a week, that is about 168 hours, and we give the forecast of our model for the next 24 hours. Then the second model data set that we used was a traffic data set, which basically tells us about the occupancy on a row of a road in US, and it also aggregates on an hourly level as per the electricity data set with the same lookback window and the forecast horizon. So these were the first two data sets. Then the third one was a retail. So it was taken from a Kaggle competition data set of a favorite, basically grocery sales, and they forecast these log product sales 30 days into the future using the 90 days of the past information. So you can see the variability in different setup and different data sets is there. Now the fourth one was these volatility. It was the most difficult of these data sets, because the first two were the simpler ones and these two were very difficult ones. When we talk about volatility, it contains the daily realized volatility values of 31 stock indices. 31 stock indices, and they were computed from the intraday data along with their daily returns. So basically in this case, what they considered was they considered the forecast over the next week, that will be the next 5 business days, using the information over the past year. So the look back time was the past 1 year, and we were giving the forecast for the next 5 days. So in this case, the look back period was about 252 days, and the forecast time that we are giving was the 5 days. Now, what's special about these four data sets was the first two data sets, that is electricity and traffic, they were the univariate data sets. So what happened was, in these data sets, there was only one variable in the input, or maybe information regarding that one variable should be kind of distributed into 3 to 4 variables, and then one output variable. So they were univariate in nature. But these last two data sets, they were kind of multivariate in nature. You can have their sources, and you can see how they vary and kind of how they have been incorporated or kind of passed up or basically stacked up into our model in the real paper that we will provide the description in our video. So yeah, the last two data sets, they were more complicated because they were not univariate, they were multivariate in nature. Also, the forecast time and the look back period was different for them. So using these four different of data sets basically give us the overview of how a model is performing and how a model is comparable to other techniques that we use about. Okay, so yeah, let's see that how our model basically perform on these four different kind of data sets, and was it comparable to the known methods we have right now or not. So yeah, let's move to the performance of a model on these different data sets. So, first of all, we have to know that how the training was done on these different data sets and what is the procedure that we followed during the training method. So, yeah, the most basic one is our data sets were divided into three parts, that is training, validation, and testing one. So, training data was used for, give our model the sense of data that how it is to train its parameters. Then validation data set were used for the tuning of our model, tuning our hyperparameters, and then testing was to know that how a model is performing on these data set. So yeah, then first our model was trained. So the thing was, the our model that we are basically providing us, or basically we can say offering to our research domain, then this model should not be that much computational demanding that it basically out resource the researchers and we cannot use it. So to basically take care of that also, when this testing was done, this was done on a single GPU unit. For example, when we did this paper, the researchers did this, handle the data sets with a single GPU. They give a timeline of the data like that. If they uses this NVIDIA Tesla V100 GPU, then the optimal time of a TFT model take for the electricity data set we talked earlier, it takes slightly over 6 hours to train, and that is very less when we talk about training transformers, while the each epoch being roughly around 52 minutes. So yeah, it was learning more about the data, its the temporal dependencies and everything. So yeah, it was a very good time to train, and each epoch was around 52 minutes. That was good for a transformer based network. Then after training there was also an issue of this, during training there was an issue of this getting better hyperparameters, because hyperparameter tuning is also a good thing, or a required thing to do when we have a large model. So what researchers did was they take basically a large domain of this state size, dropout rate, mini batch size, and then also they give the learning rate sizes, or all the possibilities that they can have, and so that they can get a fine-tuned parameters to give as an input to our models. Also, the number of heads I'm saying here is ranging from 1 to 4. So 1 to 4 is the multi-head attention that we talked about in the previous slide. They also check that how many number of heads would be more suitable for our optimal training of our model. So yeah, that's all about how the training was done and how training procedure was done on our different data sets for our these temporal fusion transformers. Let's go to the results parts now. Okay, so when we comes to the results section, the thing we basically notices was, first we will be seeing the electricity and the traffic data sets, because as I have told you, these two data sets were the simpler ones and were univariate in nature also. So the first table you are seeing here, the we are basically comparing the P50 losses on these different models that we have seen till now and discussed in the previous slides, and you can refer to the original paper also, and kind of learn about them in a sequential manner somewhere else. But the comparison here clearly shows us that the losses, for example, these kind of regressive models like ARIMA, our TFT based architecture had an advantage of 180% lower loss as compared to the ARIMA models in electricity data set basically. And after that, there were other these very popular models like deep AR, DSSM that we talked about, then the sequence to sequence and MQRNN. Also we had a significant what we can say is advantages when we compare the losses, the 50% losses of our temporal fusion transformers to all these models. So here we can see how our temporal fusion transformers performed very way better in training, and after then the at the testing section they outperformed all these models, how it was so significantly basically outperformed these previously known mechanisms to us. Then in the next slide, sorry, next, not the next slide, the next table, when we compare the P90 losses, we can also see that in this case also Arima was outperformed, then ETS, then this Deep AR, they are all these Deep AR and other models were totally outblown and outperformed by our temporal fusion transformers. So it basically shows that all the predictions, or all the things that we promised earlier, that temporal fusion transformers with this novel approach of architecture and this better approach of capturing the the dependencies between the data were not in this vague promises. They basically outperformed the the known parameters to us, and known architectures to us. So yeah, it was quite promising, and it basically, we can say it, yeah, it gave the results that we expected out of it. Now let's see the other two data sets and how they performed on it. So yeah, in this case, when we talk about this volume and retail data sets, which I told you earlier, were the more complex data sets with a more number of variables. They were multivariate in nature. Also, their look back period was different. Their focus time was different. So they were, given more complex kind of a data set to see that how our this proposed architecture will be performed under that. So you can see in the results also that our temporal fusion transformers were very close but improved as compared to these MQRNNs, and also and as compared to the popular choices like DPAR, they had a good, we can say this was a slight or a very good improvement when we come to these data sets like volume and retail, and these P50 losses. In case of P50 losses, the improvement was more, but in case of P-analysis, it was slightly comparable that how they were performing. So the basically, the basic takeaway from these results and comparisons is that yeah, the TFT basically capturing these temporal dependencies of input variables, handling these diverse inputs. It's not only promising them in vain, but also delivers us with a very good results. So yeah, in summing it all up, we can see this architecture was a novel approach, and it is totally, you can say it actually outperformed the available kind of architectures we had till date. So yeah, it was a quite a great approach, and it delivered on it what it promises it will be doing. Okay, now let's see what we had next. The next thing was the results of interpretability that we were talking about from so long. So in these tables, the interpretability of our static variables and our past inputs that were known up to the time t only are given, and all the values with weights of more than zero point 0.1 are being highlighted. So you can see clearly that in case of static variables, what is a particular store number and what is a specific item, these things were given the more weightage. So it totally makes sense because the location of a store and what is its location, where it has been working from so long, so these things basically affect the sales of a particular store also. And when we talk about these past inputs, so yeah, you can say here how these national holidays and in which month we are trading, also in which month we are selling products, they had a very high weightage, and very high sales were kind of found in those kind of variables or in those kind of scenarios. So here we can say the interpretability results were making totally sense of what results we were getting in our forecast, or in our what we say is in our quantile forecast. So yeah, interpretability basically given us the kind of the overview of how our result section is working, and how our model is predicting the outputs. Is it doing well or not? So from these values, we totally found that yeah, it's getting accustomed and kind of interpreting the these our sales data set very easily. Now coming to the different kind other kind of inputs. So the inputs, which were the future inputs basically refers to the inputs which were known from the time t to the t plus tau that I told you earlier in the slides. So in the future inputs, you can also say is that when there was on promotion, the things were there, and the particular days of the month, there were some national holidays, and then there are also some local holidays. All how all these things affected our forecast of the model. So yeah, this interpretability basically tells us more the kind of transparent picture of how our model is predicting the future. So in conclusion, we can say that our temporal fusion transformers provide us with a powerful and versatile solution for time series forecasting by incorporating these diverse inputs, interpretable attention mechanisms, capturing persistent temporal patterns, and utilizing gating mechanisms. TFT delivers accurate and reliable predictions across a wide range of application. And next we will be seeing all the references that we use in this paper. So these are all the references that were used in this paper, and we'll continue also. Yeah, and you can find the link to the original paper in the description of my video also, and find out more about this paper from. So yeah, in end, I will be saying thank you for watching this video, and I hope you found this exploration of temporal fusion transformers insightful and valuable. Stay tuned for more exciting topics in the world of machine learning and data science. Thank you.